students, this is Dr. Aisha Nazuk here. Welcome back to my channel Rao Hub, which you know is a holistic learning and, by the way, entertainment portal, because apart from my lecture series, I have some interesting playlists on which I upload videos related to human behavior, sometimes related to humor genre as well. So that's why the name of the channel is Rao Hub. So it's a holistic learning and fun channel. You can side by side with serious concepts. Sometimes you can have an occasional video from a humor playlist. So there are many playlists on this channel, ranging from probability theory, introduction to statistics, to introduction to econometrics. Then I have a playlist on GRE, that is graduate record examination related questions as well. Those of my viewers who have supported the channel so far, I would like to thank them. And those of you who have landed first time on the channel, you are more than welcome to please subscribe and share the content in your social circle. With this, I start the contents of today's lecture, which are related to the idea of Bayes' theorem. So in today's lecture, we are going to discuss what is Bayes' theorem. By the way, if you haven't watched earlier lectures on probability, or if you don't have sufficient background of probability, then it's highly advisable that first you develop your understanding of the basic concepts of probability by watching my earlier video series on probability. And you can also explore my introductory statistics playlist that will help you understand even the ideas of probability. Okay, so we will be discussing Bayes' theorem and the relevant concept like prior probabilities, posterior probabilities, and then the idea of total and conditional probability. So as the word suggests, prior means that we don't incorporate any information and we calculate probabilities in their actual form prior to occurrence of any event. Whereas the idea of posterior probability is when we incorporate some given information and then we update our estimates of probability. So we will understand what is the difference and how mathematically we can differentiate between prior and posterior probabilities, and then we will develop an understanding of total probability and conditional probability. By the way, for effectively using the contents of this lecture, it's highly advisable that you download the book which I have mentioned here, authored by Paul Newbold, and the other author names are also mentioned here. The title is Statistics for Business and Economics, and you can easily download this book from the Genesis library. So if you haven't heard about Genesis library, it's a very useful online public library from where you can download books, and by the way, you can download interesting novels as well. I mean, it's one of my favorite libraries. All the latest books, I mean not all but many latest books are available here. And if you want to know more about this library and how to download books from this library, you are more than welcome to explore my video whose title is How to Download Books from the Genesis Library, whereas I have already told you that my channel name is Rao Hub. Okay, so we will be using chapter 3 of the book that I have just mentioned. And for a more focused understanding, let me tell you that I'll be discussing contents from section 3.5 of chapter 3, and you can specifically refer to page 136 onward for Bayes' theorem examples. The only issue with this book is that the exercise solutions are not given at the end of the book. So if you want to do prepare from an, let's say, exam point of view, you can focus on the solved example. And if you want to do additional practice of Bayes' theorem, there are countless solved examples available on the internet. For example, I have shown one URL here from where you can you can do practice activity. So you are more than welcome to explore Bayes' theorem solved examples by simply typing in search engine and you can find out many examples. Some of the examples will be discussed in today's lecture slides as well. Okay, so before I set down, in fact, let me set down the foundation concepts that will help you, set the foundations for Bayes' theorem. So whenever we do some testing, let's say, for example, if I test whether a disease is present in a patient or not. I mean, it's a routine scenario that people go to, let's say hospitals or health center to get themselves screened for a particular disease. So sometimes they don't have the disease, but the test declares that the disease is there, and vice versa. Sometimes a person has a disease, but the test fails to, detect that disease. So, I mean, generally in health sciences, researchers try their best to minimize these types of error. But you know that in any testing scenario, it's impossible that you have 100% accuracy. So there is always a chance for false positive and false negative type of error. So what is a false positive and what's a false negative, I will explain with the help of a interesting diagram here. For example, there is a lady who's claiming that she saw a unicorn, right? Here I would like to introduce two concepts, H0 and H1. That is, H0 is the null hypothesis and H1 is the exact opposite of the null hypothesis. It is called H1. So let's say that we say that the null hypothesis, or the scenario in the null hypothesis, is that actually there was no unicorn, whereas in alternate hypothesis we have the statement that there was a unicorn. Now let's say the reality is that there was no unicorn, right? And the girl declares that she saw a unicorn. I mean, people can have visual illusions as well, right? So the error of concluding that there is something present, right, when in reality there is not. So we call it false positive. Just for the example of disease, if the test declares that there is a disease when actually it is not there. So that's the false positive or the alpha error. An exact opposite type of error is the beta error. It's the error of concluding that there is nothing when in reality there is. For example, there is a guy in this picture who is claiming that smoking doesn't cause cancer, right? And let's say the reality is that smoking causes cancer, right? So the guy is, refuting reality. I mean, in reality, smoking causes cancer, but the guy is saying no, it doesn't cause. So that's an opposite type of error, and we call it the false negative error. Like he's saying that nothing will happen. In reality, things will, smoking will influence or the likelihood of cancer. So this is called beta error, right? So whenever we have any testing procedure, I mean, any testing procedure is always prone to these two type of error. We always try to minimize both these errors, but they are always there. So although specifically in the series of probability theory or the playlist of probability theory, we are not going to specifically focus on in detailed concept of hypothesis testing. Maybe we'll discuss those in as an introductory or basic level. But where are these concepts used? Why am I telling you about false positive and false negative? The reason is that these ideas or these concepts will be used in Bayes' theorem, and these will also, I mean, on a side note, let me tell you that these ideas are also used in hypothesis testing, development of confidence interval, and other type of statistical procedures such as ANOVA and t-test. So we will see how these type of errors, they play their role in an understanding of Bayes' theorem. Okay, so Bayes' theorem, it was proposed by an English statistician named Thomas Bayes, and that's why, because of his surname, we attribute the theorem with the name Bayes' theorem. So it provides a way of revising conditional probabilities by using available information. So what does that mean? That we are going to use an available information and we are going to update our estimates of probability. So by the way, once you do some examples of Bayes theorem, maybe then you can refer back to this definition and you'll understand it in a lot better way, rather than I emphasizing on it theoretically. So let's do some examples and then the idea will clarify. So before the example, just a schematic layout of the Bayesian procedure, that we start from the prior probabilities, that is probabilities in their actual form, and then some new information enters in the system. We apply the Bayes theorem, and we update the estimates of probability, and then we call those probabilities as posterior probability. So the process starts from prior probabilities, and the terminal node of the process is the posterior probabilities. So here's an example. That those of you who have an interest in Olympics, you must have noticed that whenever an athlete apply or is included in an Olympic competition, they have to pass a certain type of drug clearance test. Some of the countries, they have their their own reservations that they don't want to undergo a drug detection test, because there are of course legalities and ethics involved with those type of tests. Anyways, that will be a digression from our main topic. We are concerned with the statistical understanding of Bayes theorem. So anyhow, whenever an athlete is included in a competition, they undergo a drug detection test, that is in order to enhance their performance, whether they have used a drug or not. So let's say 10% of the athletes seeking participation in an athletic union have used a performance enhancing drugs. So if you randomly test one athlete and you check the probability that they have used the drug, so on a random test, detection of drug probability is 0.1, which is sort of a prior probability. Now, in addition, suppose that a test is available that correctly identifies an athlete drug usage 90% of the time, right? 90% of the time, the test is able to correctly predict the drug use. So if an athlete is a drug user, then the probability is 0.9 that the athlete is correctly identified by the test as a drug user, right? So as I said that there are two types of errors, so we have here two types of conditions. If an athlete is a user, then what's the probability of a correct decision? It is 0.9. Similarly, if athlete is not a drug user, then the probability of correct decision, that is declaring that he is not a drug user, that is again 0.9. This is just by chance that here these two probabilities are same, but they could be different as well. So let's put this diagram, data in the form of a tree diagram. So before I refer you to the tree diagram, let's classify the two level of information that we have. D1 is an event that the athlete is a user of drug, and D2 is the athlete is not a user of drug. T1 is the output that the test says that athlete is a user, right? Whereas T2 is the output of the result or the test which says that the athlete is not a user of performance enhancing drug. So these are the two level of you can say bifurcation or dichotomy, that is either the person is a user of drug or not. Similarly, the test declares that the person is a user or not. So once we put these in the form of a tree diagram, you see what I have done, the initial bifurcation is from whether the person is a drug user or not. So I have put the probability of drug user as 0.1. And why it is 0.1? If you refer back to the statement, you see it was given that 10% of the athletes are using drug. So that's why I've written here that probability of using drug is 0.1. So probability of not using drug, so let's call it D2, as I have already given this notation. So not a drug user is 1 minus 0.1, which is 0.9. So 10% are drug user and 90% are not drug users. Now, irrespective of the status of the athlete, the test can classify the person as a user of drug or non-user. So if the person is a drug user and the test declares that the person is a drug user, so that's a true decision, right? And it's given here in the question, if you refer back, that if the athlete is a drug user, then the probability of correct decision is 0.9, that is the athlete is correctly identified as a drug user. So that's why I have written here that the true decision, in this case the probability is 0.9, and I'm calling it conditional probability of test declaring a person as a user given that he is a user. So this is a true decision. Now the second branch is that the test says that the athlete is not a user. Now this is a false decision, right? The person is a user whereas the test is saying not. So this is false negative, that the problem is there but the test says no, it's not there. So now we know that 0.9 or 90% are the chances of true decision. So here in this branch, the probability of incorrect decision or false decision, that will be 1 minus 0.9, because here we have two bifurcation. So sum of the probabilities in these two branches should be 1, just as the sum of probabilities on the first level of bifurcation, that should be 1, like 0.1, 0.9. Similarly here, if we have the first branch labeled as 0.9, then the second branch should be labeled as 1 minus 0.9, which is 0.1. Now focusing on those who are not drug user. So refer back to the statement, if the athlete is not a drug user, once again the probability of correct decision is 0.9. So I'm going to fill it here. Now what will be the correct branch, the last one, because the person is not a drug user and the test says that he is not a drug user. So it's given in the question that this probability is 0.9. So it's a true decision. Now the third branch is that the test says that athlete is a user whereas in actual he is not. So that's a false positive. I mean the problem is not there and the test declares that there is a problem. So it's a false positive and it is equal to 1 minus 0.9, which is equal to 0.1. So here, if as I label these events as D1 and D2, similarly T1 means that the person is declared as a user. So T1 given D1 would mean that the the athlete is declared as a user given that he was using drug. Now if I multiply 0.1 with 0.9, what would that mean? It would mean that the person is a drug user and he is classified as a drug user. So this is probability of D1 and T1. This inverted U symbol is read as AND or intersection. So that means both conditions are met, that the person is a drug user and the test declares that person as a drug user. So you can see it is equal to the probability that the person is a drug user, which is 0.1, multiplied by the conditional probability that the test declares that person as a drug user given that he was drug user. So I am focusing on the first branch. So 0.1 multiplied by 0.9, so that gives me 0.09. Similarly, I can fill all these branches. So T1 and D2 will be D1 and T2. So that will be D1 and T2. So the second branch. So 0.1 multiplied by 0.1. So that's 0.01. Similarly, so we can fill out all these probability scenarios, and depending upon what is the question, you can easily answer the required value. So after this tree diagram, we can also fill a table in which we can enlist all the probabilities that we have just calculated. If you see, the first probability is that the person is a drug user and the test declares that person is a drug user. So if I make a 2 by 2 table, so we have two scenarios or two results of the test. T1 means the test says drug user, T2 says the test says not a drug user, where the actual status of athlete are drug user or not a drug user. So we have just calculated that if the person is a drug user and the test says that he is a drug user, it is equal to 0.09, right? D1 and T1. Second is D1 and T2. So D1 and T2, you can see the answer is 0.01. So D1 and T2. So I have filled that entry here. So what I have done in the tabular approach is simple, that whatever the answers of the all possible branches are coming from these tree diagrams, I have enlisted those in the form of a table. And now you can see that if I add the probabilities, these two probabilities row wise, so this 0.1 is the probability that the person is a drug user. Of course, it all started in the beginning. You could see that the probability is 0.1. So that's sort of a calculation check as well. So if I add these two probabilities, it will be 0.1. Similarly, probability of not drug user, if I add these two probabilities, so if I have calculated these correctly, they should sum up to 0.9, which was the start of this condition, not a drug user. Now if I add the probabilities column wise, so that will be the probability of test declaring a person as a drug user, which is, so this is the total probability. So this is 0.18 is a total probability of declaring someone as a drug user. It includes correct decision as well as incorrect decision. Similarly, 0.82 is the probability or the total probability that the test says not a drug user. So if I add these two probabilities, they should also add up to 1. So it's sort of a calculation check as well. Now if I calculate the probability, I say that the condition is given that the athlete is a drug user. So it's given that the person is a drug user, or he or she is classified as a drug user, because T1 means test says drug user. So D1 given T1 means drug user, T1 means that the person is classified as a drug user. So it's a probability of correct classification, or it's a posterior probability of correct decision, which in this case is D1 given T1. You know that the rule of conditional probability, whenever we have to calculate conditional probability, we take the intersection in the numerator, and in the denominator we have the probability of the information which is given. So here T1 is given, therefore in the denominator I have probability of T1. So D1 and T1, you can see it is equal to 0.09, and probability of T1, as I have just calculated the sum of these two columns, it is 0.18. So this is the posterior probability of a correct decision. Now similarly, if I have to calculate the probability that it is given that the athlete is not a drug user, what is the probability that he or she is classified as a non-user? So similarly, the posterior probability, if it is given that the athlete is not a drug user, that is the given condition is T2. So what is the probability that the test declares that person as a non-user? Once again, it's a correct decision, and you can see I have taken the intersection of D2 and T2. So D2 and T2, so you can see it is equal to 0.81, and I have divided it by probability of T2, which is 0.82, based on the sum of these two values, right? So this is how we have seen a typical application of Bayes' theorem. Here in this scenario, you can see that this test needs a lot of improvement. Why? Because you see here the probability of a correct decision is only 50% or 0.5. So that means there is 50% likelihood of incorrect decision for those who are users, and for those who are non-user, that probability is okay, fine, that's low, because 1 minus 0.988 will be a lesser number, but here 1 minus 0.5 will be 0.5. So 50% is correct probability, then there is a possibility of incorrectly classifying someone. The person is a drug user and he is classified as a non-user, so that probability is quite high. So that means if the person is in the start of the question, you see that the probability of declaring someone as a drug user, it is 0.1. But here if I say that the test says that the person is a drug user, and he is classified as a drug user, that is 0.5. So exact opposite, that probability is again 1 minus 0.5. So we have 50% likelihood of incorrect decision. So that's why this test needs massive improvement. Anyhow, so what we have done, we have just seen a numerical application of Bayes' theorem. You can see that here when I am calculating these conditional probabilities, then you can see that I have used this intersection. So how this intersection is calculated? Refer back to this slide. The intersection is calculated by using a simple probability and a conditional probability. So you can see that the Bayes theorem says that if we have to calculate a conditional probability, we have to use the total probability of given condition in the denominator and a multiple of a conditional probability and simple probability of the event. So you can see if we have probability of B1 given A1, then in the numerator I have product of opposite type of conditional probability. If it is B1 given A1, then we have probability of A1 given B1. Similarly, I can restate or express the theorem in the form of A1 given B1. So if I have to further expand this denominator part, probability of A1, like for example here when I have calculated 0.18, it's a sum of two possibilities. If you refer back, it's a sum of two branches in this tree diagram. So here what I'm saying is that the probability in the denominator is you can see it's part of the numerator. In fact, numerator is a part of denominator. If you see probability of A1 into probability of B given A1, this is exactly the first term in the denominator. So that means that event B occurs given that A1 has occurred, but event B can also occur in the presence of another type of event which is A2. For example, here if we have look at this tree diagram, then the output that a person is declared as a drug user, it can happen both in the case when actually he is a drug user or he is not a drug user. So we have to add two type of branches to get the denominator. So that's why in the denominator you see we have two terms, and numerator is always part of the denominator. So this is the Bayes theorem for the two event case. We have another example for further explanation. Let's say 65% of the parts purchased by a company are from supplier 1 and 35% are from supplier 2. Now there is a probability that if the supplier 1 provide, in the history supplier 1 has provided 98% of the time he has provided good parts and 2% of the time he has provided bad parts. Similarly, supplier 2, 95% of the time he has supplied good parts and 5% of the time he has supplied bad parts. Now let's say in presently what happens, it is given that a randomly selected part was found to be bad and you want to calculate the probability. Suppose you don't know that who supplied that part and you want to find the probability that which was the supplier who has provided this bad part. So now I have probabilities. So let's say I enter these in this information in the form of a tree diagram. So here 65% is the probability that it was supplier 1 and 35% the probability it was supplier 2. Why? Because in the question it is given that 65% of the parts are from supplier 1 and 35% are from supplier 2. So let's focusing irrespective of these notation, let's focus on the conceptual details of this tree diagram. So if 65% is the probability that supplier 1 provided the part, now it's given that in his historically 98% of the time he has provided good parts. So 0.98 is the probability that the supplier 1 has provided good part. So opposite of 0.98 is 0.02. And it's also given in the table that 2% is the probability that supplier 1 provides a bad part. So now we have filled this first branch or the first part of the tree diagram. Similarly, we can fill the second part based on the given data, as you can see 0.95 and 0.05. So now I have this tree diagram available. Now I can easily calculate the probability. Now you see what was the question. It was saying that this is given that the part was bad. and now we have to calculate the probability of supplier 1 or supplier 2. So basically there are two parts of this question. So if I focus on the first part, so what is the probability that supplier 1 provided it given that it was bad? Because in the question it is given, it is known that the part is bad. So probability of S1 given that it's bad is equal to probability of bad given that it was supplied from supplier 1 multiplied by probability of supplier 1, and in the denominator we have the total probability of a bad part. Now probability of supplier 1, you know it is 0.65. As you can refer back, we know that 65% of the likelihood that supplier 1 provided part. So 0.65 is the probability of supplier 1. Then probability of bad part given that it is from supplier 1. So it's given it is 0.02. As you can see, probability of bad from supplier 1 is 0.02. As you can see here from this data as well, that 2% of the part are provided bad from supplier number 1. So now what is the probability of bad part? Here I am going to add probability of bad from supplier 1 plus probability of bad from supplier 2. So I am going to add the two branches, 0.65 multiplied by 0.02 plus 0.35 multiplied by 0.05. So you can see that the numerator is part of denominator. So if you solve this, it comes out to be 0.4262. So approximately 43% chances that the bad part was supplied by the supplier 1. Now if I have to calculate the probability that the bad part was supplied by supplier 2, I should know that it should be equal to 1 minus 0.4262 because we have only two suppliers. So if the probability of supplier 1 providing the bad part is 0.4262, so the probability of supplier 2 will be 1 minus 0.4262, and you can easily calculate using Bayes' theorem once again. So here you can see that if we have to calculate probability of supplier 2 given that it was bad, so you can see here I have input in the numerator the probabilities or the branch which was coming from the supplier 2, which is 0.35 into 0.05. So you can see either you can directly subtract it from 1, the probability of supplier 1 from 1, or you can calculate using the Bayes' theorem. So if I once again input the data in the form of a table, the prior probability of supplier 1 was supplier 1 supplied the part is 0.65, and the prior probability that supplier 2 supplied the part is 0.35. Now conditional probability of a bad part from supplier 1 is 0.02, and the conditional probability of a bad part from supplier 2 was 0.05. So prior probabilities and conditional probabilities were given, and the last two columns, that is the joint probability and the posterior probabilities, we calculated these. So what is the joint probability? We multiply 0.65 by 0.02, so that's the probability that the two events are occurring together. So once I divide the joint probability by the total probability, which in this case you can see the total probability is simply the sum of these two numbers. So this is the posterior probability. In simple word, this 0.4262 is the posterior probability of a bad part coming from supplier number 1, and this 0.5738 is the posterior probability of a bad part coming from supplier number 2. So you can see that the prior probabilities of supplier 1 being chosen or supplier 2 being chosen, they were given. You had conditional probabilities, and then you made use of the available information. In this case, the available information was that the part is bad, so you use the probability of a bad, as treated that as a given event, and then you updated the posterior probabilities. So this is the concept of posterior probabilities explained here with the help of this tabular approach. So this is the end of video lecture on Bayes' theorem. The NAS students who watch my lecture series, they are they're side by side enrolled in a face-to-face teaching mode course as well. So they are using these resources in parallel to my face-to-face classes. But general viewers are welcome to post their queries if they have any regarding this lecture. If you want me to email you these lecture slides, you are more than welcome to drop me an email. And as I said, you are more than welcome to explore other videos in this channel. So thanks you once again for watching this video lecture, and I hope it's going to support you in your learning endeavors.